Okay, so I'd like to demonstrate the three main modes of mechanical deformation involving shear of planes of atoms. I have a face-centered cubic structure here, close packed plane, a 1-1-1, close packed plane, another 1-1-1 plane. I start with simple shear. Simple shear involves the translation of one volume of one half of the crystal, call it a half, or one segment of the crystal relative to another. So let's take the three bottom planes here and then shear the top layer against that. This involves the passage of a dislocation. In this case, the dislocation, the full passage of one perfect Burgers vector is a half 110 Burgers vector, but it's comprised, it goes in two steps because there are two intermediate sites where the atoms can sit nicely. So that's and these involve 1611 bar 2 partials, Shockley, what's called Shockley partials. So there's the slip mechanism, two Shockley partials giving a full lattice displacement. So the main thing to understand here is that the passage of a dislocation doesn't change the orientation of one part of the crystal relative to the other. It just translates one part of the crystal relative to the other. This is important in many respects because there's a mistaken belief that it does, but it's kind of a misguided belief. Okay, the second mode of deformation involving shear is twinning. Now, twinning involves the shear not just of one half of the crystal, but each successive plane. So, and we use these, it's also each successive plane by these partial dislocations, which are Shockley partials. So if we move each successive plane by one partial, let's go in this direction. 1, 2, 3, 4, 5. I've sheared the crystal. So we've gone from a close packed plane now to a plane which is not close packed. In this case, this is a 100 plane. The plane that we started with was a 1-1-1 close packed plane. So the important thing to note here is this bulk shear causes a change in the orientation of the crystal. So I'll put it back to where we started from. And we have that change in the crystal orientation. The other form of plastic deformation involving a shear is a Martensitic shear. Now, a Martensitic shear is somewhat similar to a twin shear, except it involves shear on each alternate plane. So if this is our base plane, we can shear the next plane up, number 2, and 4 and 6. So if we apply a Martensitic shear to this crystal, what we do here is move this plane, miss this one, move that plane, miss this one, and move that plane. So it's basically half the shear that you would get in a twinning operation. But the important thing to note in a Martensitic shear is that not only has the crystal orientation changed, but the crystal itself has changed. We're now a 10-bar-1-1 plane in a hexagonal close packed crystal. The crystal has now become a hexagonal close packed structure, although it started off as a face-centered cubic structure. So we can reverse, just like with a twin, one can reverse that shear transformation again on every successive plane. So we'll start with shearing this plane that way, this plane that way, this plane that way. And we're back to our original 1-1-1 close packed plane in a FCC crystal structure.